Welcome to the second of Fiala Shanahan's LOEB lectures. Those of you that heard the talk yesterday know that she's a wonderful speaker, and I personally was very excited to hear about the synergies between lattice gauge theories and experiments, and I hope that she makes good on some of the teasers from the last talk today. I wanted to say that as much as we would like to listen to Fiala every day, we have to skip a day. The last talk is Thursday. Finally, if you have questions after the talk, please raise your hand so we can get a microphone to you. With that, I will turn things over to Fiala.
Thank you very much. So it's really a bit of a rare pleasure to be able to give a series of talks that's not, say, summer school lectures or something like that. And so I'm going to really enjoy going a little bit more into some of the details I hinted at during the colloquium yesterday. And the thing I'm going to focus on today in particular is a few new things we've learned about the quark and gluon structure of the proton. Okay, so for those of you who are at my colloquium, I sort of broke down the various questions we might ask about the quark and gluon structure of the proton into three different pieces. I said we can look at its sort of basic, more static quantities. How do the quarks and gluons create the proton's mass, its momentum, its spin? I said, well, going beyond that, what about the three-dimensional distribution of quarks and gluons inside a proton that's encoded in things with names like form factors and distribution functions? And I also talked a little bit about what happens when you bind protons and neutrons together into nuclei. Today, we're really going to talk about just a couple of aspects. I've chosen just two that fall into this middle category, which are gravitational form factors and the Collins-Soper kernel. And my goal for today is two things: to give you really an idea of what the new results are, how they interface with the experiment, but secondly, since I have a bit of extra time, I'm going to also tell you how you get them from Lattice QCD calculations. And part of the reason for doing that is that if you're not a lattice practitioner, which I think probably applies to most people here, it's important to really know what the error bars mean if you look at theory calculations, including lattice calculations, and what it means when you try to compare them to experiments. So I'm going to take just a little bit of extra time to try to explain that as we go along. All right, so one of the big motivating questions I had during the colloquium was that we can now start to answer some of the sort of qualitative, previously unanswered questions about the proton structure, like what's the gluon radius of a proton and how does it compare to a quark radius? And I explained that if you look to models for guidance, you have different answers. And so it's really that we need to do calculations and measurements to answer these sorts of questions. So for those of you who were here yesterday, this is a slight repetition, but just to emphasize, if you take different models of the proton, if you take a bag model where the gluons expand to fill the bag, you might say the gluon radius should be larger than a quark radius. If you take a constituent quark model where the gluons hide inside massive quarks, maybe you say they're similar. If you see gluons emerging in flux tubes as you pull quarks apart, you'll say maybe it should be smaller. And so what is the answer? How do you define this? These are the sorts of questions that we're trying to answer, and we're beginning to answer just in the last year or two. Okay, so I'm really talking about this from a theory perspective, but there really is a great synergy and complementarity with experiment. And it's not like these are experiments done many years ago that we're now doing theory calculations just to catch up to. It's sort of a rare opportunity that I don't know how many times you get to do this in a career, where my students and I calculated something for the first time, and a month later was the first experimental measurement of that quantity. So it's all happening at the same time. So right now, a lot of these experiments are being done at the Thomas Jefferson National Accelerator Facility, that's in Virginia. But the electron-ion collider is also under construction, so that will be the United States sort of new big nuclear physics experiments over the next 10, 20 years. And you can see on the front page of the white paper for the electron-ion collider, maybe the text is a little bit small, but it's sort of tagged as understanding the glue that binds us all. So a lot of these questions about the gluon structure of protons, neutrons, and nuclei will be measured for the very first time at that machine. So it's really sort of now that both theory and experiment are making advances on this front. Okay, so going into a little bit more technical detail, we're talking about the three-dimensional structure of the proton. How do we describe that? So there's a number of different distribution functions. So the parton distribution functions, or PDFs, what those really are is this is the number density of quarks of some flavor Q in a hadron, like the proton, of type H, carrying some fraction x of that hadron's longitudinal momentum. So here's a proton, it's zooming along the z-axis here, and here's a quark of some type, some flavor Q, and that's carrying a fraction x of the proton's longitudinal momentum, right? And this is just the number density of quarks in that category. So that's one type of distribution describing the proton structure. As you can tell, I talked about longitudinal momentum, so this is really only a one-dimensional picture still. It's only talking about the fraction x. There's only one variable here, of the proton's momentum. So of course, there are other distributions you can write down if you think also about the transverse structure. So what about the momentum transverse to the direction the proton's moving in? That gives you more distributions called transverse momentum dependent, TMD, parton distribution functions, also called TMD PDF, so a lot of acronyms, right? Okay, as well as the transverse momentum here, you can think also about the impact parameter. So this distance here, BT. You can think also about a momentum that you might transfer to that struck parton in a scattering process, which can be encoded in the overall momentum scale and a longitudinal piece. I realize not all of these things are defined precisely on this slide. That's because we're talking more about it right now. We're going into more details on GPDs, which are called generalized parton distribution functions. So in some sense, it's just a more general distribution of quarks and gluons inside the proton that depends on several variables, not just the one that the PDFs have. Okay, now I want to dig into one particular part or aspect of the GPDs, which are called the generalized form factors. And I'm defining that on these slides, and then on the next slide, I'll give you something to hang on to, so something like why you might care about these. But first, the technical details. So gravitational form factors are one aspect of generalized form factors. It's convenient that the acronyms are the same, GFF, right? But they're related to these GPDs, which are these generalized parton distribution functions, which I'm defining in their sort of full glory here on this slide. So to break it down, we have a state, let's call it a proton, with momentum p, spin s. On this side, momentum p prime, spin s prime. In the middle here, we have gluon field strength tensors, and they're separated along some light cone distance, right? Indexed here by lambda, and then I have an adjoint Wilson line in between them. If you write out what you get from that, well, you get some number of different Lorentz structures. You get these spinners, U and U prime, and then you get some Lorentz structures, P's, gammas, right? This P is the total momentum, delta is the momentum transfer defined here. You just write down every possible Lorentz structure you can. You have some a priori unknown coefficients out the front, and those coefficients, those are these generalized parton distribution functions. Okay, if you take them and you integrate over this longitudinal momentum fraction x, you get some more a priori unknown functions, and these things are what are called the generalized form factors or gravitational form factors. So why gravitational form factors? Well, in some sense, they encode what you would get if you did graviton scattering off a proton, right? It's something, you have your spin-2 interaction. Of course, you can't do graviton scattering, so you have to get at them through other experimental processes, maybe using 2 photons to get at the same sort of spin. But that's what they describe, much like an electromagnetic form factor describes what you see when you do electromagnetic scattering, say scattering a photon off a proton, right? Okay, so how else can we see what these gravitational form factors really are, what they mean, what they encode? Well, you can also see them coming out as matrix elements of the energy momentum tensor. So here I'm writing down again, this is a proton, momentum p, spin s. These are gluon field strength tensors, so together this is the gluon part of the energy momentum tensor. And if I write down a decomposition, and again, we're doing exactly the same thing, we write down the spinners, and then all the different Lorentz structures that you can get, and they have a priori unknown coefficients. Those are the same things that we saw before. Those are these generalized form factors, these gravitational form factors, right? And so in this form, you can see, related to matrix elements of an energy momentum tensor, these form factors should have something to do with pressures, they should have something to do with shear distributions, and that's in fact exactly one way of interpreting what comes out. So we can dig deeper. So this particular gravitational form factor, A, what is it? Well, if you go to the forward limit, that is, go to 0 momentum transfer, this t is just the momentum transfer squared, so that p prime minus p squared, yeah, t is delta squared, right? If you go to 0 momentum transfer, this a is just telling you the fraction of the momentum of the proton carried by some particular type of quark, or the gluons, right? This is one of those simple static quantities that we talked about. How is the momentum of the proton generated from the quark and gluon pieces? And that's encoded inside these generalized form factors just as the t equals 0p. So of course there's a sum rule that between all of the quarks and the gluons, you must carry all of the momentum of the proton, so this has to sum to 1. What about the others? So a combination of A and B, you get exactly the same thing, but for the spin, right? So in the forward limit, so 0 momentum transfer, it tells you what fraction of the spin of the proton is carried by the different types of quarks and the gluons. It has to sum to 1/2 exactly, right? So these are sum rules. And then there's one more. There's D. What's D? Well, until very recently, we didn't have measurements or calculations of D, which feels sort of funny, right? It enters these equations at the same place as momentum and spin, which are very fundamental properties of the proton. And there's also another thing, it's called the D term, that sort of enters the equations at the same level, right? And so that's really what was driving interest here in this particular quantity, the D term and the D term form factor, is that it comes in these equations in sort of a fundamental place, and yet it had never been measured or constrained until 2019. What is it? Well, the forward limit, there's no sum rule there. It doesn't give you a quantum number. However, the Fourier transforms of the t dependence tell you about the pressure and shear distributions. And you can see that by going back to the fact that this is an energy momentum tensor. Okay, so this is one of the distributions that I want to talk about in particular. There's been a lot of development over the last few years. And that was really kicked off in 2018 by the first experimental constraints on one part of this D-term generalized form factor. Okay, so the experiments were done at Jefferson Lab, and they're constraining only the quark piece of this D-term. That's because the experiments couldn't access the quark piece. They were doing essentially a process called deeply virtual Compton scattering, but what that gets is the charge squared weighted sum of all the quark pieces. It doesn't access the gluon piece at all. And this here is the first constraints on this D-term form factor. On the horizontal axis is the t, so that momentum squared scale, right? So these things were a function of t. This is that variable, and this is this D-term, these 5 data points here. So this is connected to pressure and shear. So you go, okay, going from 5 data points to distribution is maybe a bit of a stretch, but let's give it a go. If you work through, starting from the definition of the energy momentum tensor, how you would get pressure and shear, it's a Fourier transform and then some number of these derivatives and factors of R. R is just the Fourier transform variable here. So some sort of complicated expression, but really that boils down to a Fourier transform of this function here. This is the pressure distribution that you get from the experiment. So this is the center of the proton. This is moving out along a radial direction. This is that radial distance squared times the pressure distribution. And what this suggests is that there's a repulsive pressure near the center, so this peak, and then a confining pressure, a trough afterwards, and all of it, this integrates to 0 with an uncertainty, so it leads to stability of the proton. Okay. So this was very interesting. The thing that made sort of big splashy news was that the peak pressure in the proton came out as something like 10 to the 34 Pascal, so more than estimated for the interior of neutron stars, which are some of the densest known objects in the universe. So that was sort of interesting. Would you have expected that or not? I don't think you had any reason to expect or not expect that, but it's still a cool statistic. But of course, there's a lot of assumptions that go into going from this to taking a Fourier transform of this. Also, this is only a quark piece. So really, in getting to this pressure distribution, the assumptions were, well, the gluon D term, it can't be measured, so let's just assume it's the same as the quark one. We can't separate the different quark pieces, so let's just assume they're all equal. And we need to do a Fourier transform of this, so let's just take a model of what the shape should be. And then you get to the pressure. Okay. So it was a very exciting first look. It was far from, fully controlled result. So this was very exciting from a theory perspective because there was one particular particularly key piece missing, which was any constraint on the gluon D term at all. And we'd just made some advances that let us calculate this for the first time right about the same time as these experiments. And so we're able to really test those assumptions that went into that pressure determination, and they weren't too bad. So what I'm showing here now is,
the
yeah.
pressure, the peak pressure being so large, is that not just dimensional analysis? I mean, that function doesn't look particularly unusual.
Yeah. That's why I sort of said, I don't know, this was what was, on the cover of Nature and in the newspaper articles, but it's nothing really fundamentally interesting in it being so large. It's just
Test that answer if someone didn't want.
yeah.
And I imagine it's order 1 is the pressure to test that.
Yeah, exactly. Okay, so these are D terms, but now different contributions. This is those 5 points are the 5 points from experiment, along with the model that was then Fourier transformed, this blue band. These purple points, those were some very early lattice QCD constraints, not by my group, but in the late 2000s by another group. You can see that's not particularly constraining in that region. Then these green points here were the first lattice calculation of the gluon D term. And so you're able to take these assumptions and sort of say, okay, the assumption that the gluon D term is the same as the quark in magnitude and shape, yeah, up to a factor of 2, that's not too bad an assumption. The tripole form factor model, so the shape that's fit to these distributions and Fourier transformed, is data's consistent with that ansatz, but of course if you take more general shapes, you can fit them also. And that the isovector, so the up minus down quark combination vanishes, that actually holds quite precisely from lattice QCD results. So you can take the gluon piece, you can put them together. Those assumptions were reasonably good, but you do see one qualitatively interesting difference when you put everything together. This is this cartoon again, the pressure distribution times the radial distance squared. This is the radial distance out from the center of the proton. Blue is the quark part, green is the gluon part, and you see qualitatively that the gluons have a larger radial extent of their pressure distribution than the quarks. So this was sort of the first qualitative hint of something interesting going on in this comparison. Again, very early, 1 part's from theory, 1 part's from experiment. You're trying to combine and compare the two. It's a very difficult thing to do with systematic control, right? But this was sort of an interesting feature. So since that was the status in 2019, there's been lots of rapid and exciting progress, which will be sort of the rest of the first part of this talk. And that progress, as it says here, is really first calculations with systematic control of all of the pieces to really get these answers for the first time, really being able to rigorously compare from the same framework the quark and gluon pieces. Okay, so I keep talking about lattice QCD calculations. I talked about them briefly in the colloquium. As I promised, I want to give you just enough information to sort of understand what the error bars mean. So lattice QCD is an approach to studying quantum chromodynamics, so the theory of the strong interactions, non-perturbatively via a lattice regulator. So it's in principle exactly what it sounds like. You discretize space and time onto a grid or lattice in such a way that you can solve the theory numerically. So the sort of key pieces are you approximate the QCD path integral. You're really just starting from the path integral and doing it by Monte Carlo sampling. You have to run this on supercomputers, extremely computationally expensive, and then of course at the end you have to take all of the various limits. Finite lattice spacing goes to 0. Finite box size gets large. You have to interpolate or extrapolate to get the pion mass exactly right? The pion mass is not a variable in your calculation. It comes out from setting the bare quark masses. Right? So you set the bare quark masses, you do the calculation, you see what comes out at the end, so you have to tune to reproduce the parameters of nature. Right? Okay, so we have our box. We have a Euclidean lattice spacing, which, as we'll see in the second part of the talk, makes getting at light cone defined quantities particularly difficult. But there are ways around that. And then here is sort of the most technical part of the colloquium. Is one of the entry points here is exactly what you're doing. Matrix element of some operator O. This is just our path integral. We're in Euclidean space, so there's no I here in this weighting inside the path integral. It's just the exponential of the action. You sample over the field configurations here with this exponential of the action, this weighting already built in, And then you're doing a statistical problem. You're computing means and standard deviations of resampled, you do bootstrap or jackknife resampling, but over these various measurements to get the answers. So that's the overall process. I want to emphasize, so every time I talk about Lattice QCD, I need to emphasize this, that the inputs, the free parameters, are the same free parameters as in QCD itself. As I said, there's a tuning problem. You have to fix them by matching to something experimentally measured. So you take bare quark masses, then you do your calculation, you get some hadron masses out, they're not quite right, you retune the bare quark masses until you reproduce measured hadron masses, and so those observables are gone, you use them to fix your free parameters, and then everything else are just predictions of the theory, right? You fix the bare quark masses, you fix the strong coupling, everything else you get are predictions. You do not model a proton as something with, 3 quarks. It has the quantum numbers of 3 quarks, but exactly what's happening dynamically, that's all just non-perturbative coming out of the path integral itself. Okay, so how do you actually do a Lattice QCD calculation? Well, so at the most basic level, let's think about calculating a mass, say the mass of a proton. And so what you do is you say, let's create a state with the quantum numbers of a proton at what we call the source. Then later in Euclidean time, this is not real time, this is Euclidean time, it's sort of a fictitious time, you annihilate a state with the quantum numbers of a proton. If you think about doing that, write down a creation operator and an annihilation operator, and you insert a complete set of states in the middle. You can do this essentially just a quantum mechanics problem. You can see the same result coming out. What you see is that correlation function just looks like a sum of exponentials where the exponents are the energies of the states, and this is a sum of everything with the quantum numbers of whatever the creation operator was, right? Sum over all states with those quantum numbers. So this is convenient if you want to get the ground state, because everything other than the ground state dies off exponentially faster. So if you go to very late Euclidean times, remember this has nothing to do with the time in the scattering process, right? This is a fictitious time. You're left with just a single state. This is the ground state energy, or the mass of the particle you're trying to get at. And so a particularly convenient way of showing these results is you take this is just a finite difference derivative, basically, right? Pulling out this exponent here. You can write down what's called an effective mass function, which in the large time limit should asymptote to the energy you're trying to extract. So you calculate a correlation function, you compute this log ratio, and then you have a function that in the large time limit asymptotes to what you're trying to extract. So this is a particularly noisy example. This is actually the alpha particle, so a nucleus. And for anyone who was at the colloquium yesterday, you know that they're extremely computationally difficult to calculate. I've chosen it because it's so noisy and you can really see the different regions very clearly. This is the Euclidean time. You have this exponential decay of excited states. That's the contamination from the extra exponentials here. You have some region where it gets flat. This doesn't look super flat, again, because I've chosen pretty much the noisiest and ugliest thing I can show you in calculation of the proton. There's a very long region where it's very flat. And then you get signal to noise problems, everything blows up, you don't have good statistics anymore. So it's really, in the central region here, you have a signal. You can also fit the exponential part, but that's how you extract a mass. Okay. What about matrix elements? I said these generalized form factors that we want are matrix elements of the energy momentum tensor. Well, you create a state with the right quantum numbers at some time, you annihilate it at some later time, but now you insert the operator that you're trying to take matrix element of at some intermediate time. If you do the same sort of exercise, inserting complete sets of states and so on, you can show that taking a ratio of this 3-point correlation function, 3 points, 1, 2, 3, right? 3-point correlation function, which now is a function of 2 times, the sync time and the operator insertion time, to a 2-point correlation function, gives you something that asymptotes in the limit of both of these time separations becoming large to the matrix element of the operator that you're interested in. And so what that looks like here, this is again a particularly ugly example, but it shows you all the regions very clearly. Here, this is my sync time, shown with the red dots, and this is a function of operator insertion time. So if I insert the operator too close to the source, the signal's contaminated. If I insert it too close to the sink, the signal's contaminated. If I insert it in the middle, there's this region where it's flat. That's because you have a fairly uncontaminated signal, and then by fitting these sorts of bumps, so the flat part and the exponential contamination, you can extract the matrix elements you're interested in. So that's essentially how this process works. So what are then the differences between different calculations? How do you interpret the error bars? Well, there's two pieces. There's the uncertainties on, say, a single ensemble. An ensemble is the set of the quark and gluon fields that you've sampled over in the Monte Carlo. When you do that sampling, you have to choose your lattice spacing, your box size, your quark masses, right? And so then there's uncertainties on that single ensemble. It's data volume, it's how you do the fitting, right? I showed you have to fit to these signal regions, how you do that, how do you treat the excited state contamination, how do you do the renormalization? Renormalization is something I don't have a lot of time to go into today, but essentially you have a lattice regulator and you have to convert from the lattice scheme you're in to something you can get at experimentally, like MS bar. And so there's a matching, there's a renormalization procedure that you can do also non-perturbatively there, but how is that done? But all of that, those are just uncertainties for one set of choices. One lattice spacing, one lattice volume, one set of quark masses. Then there's also the question of how you do all of the extrapolations. The continuum extrapolation, the infinite volume extrapolation, tuning the quark masses, and so on, right? So there's different layers of uncertainties. Sometimes calculation will be reported on a single ensemble, and those error bars definitely do not mean the same thing as uncertainties reported when an attempt has been made to extrapolate to everything controlled at the physical point, right? Okay, so for these generalized form factors, particularly the D term, what we're particularly excited about is new calculations at a physical quark mass, where we've been able to separate out all the quark and gluon pieces separately. We've got rigorous non-perturbative renormalization. However, we do not have control yet of the lattice spacing effects, and that's the last piece, the last uncertainty that still needs to be added here. We expect that to be small compared to the statistical uncertainties, but nevertheless, that's something that there is no calculation yet, including the removing the discretization. So this is really the PhD work of my awesome student Dimitra, who's now a postdoc at Berkeley, and Dan, who's a former postdoc in my group, who's now at Fermilab. Okay, so let's now do a calculation of these generalized form factors. We're going to create a state with the quantum numbers of 3 quarks at a source, annihilated at a sink, and now the operator that we're inserting is the energy momentum tensor. So either the gluon energy momentum tensor, here we're doing just the traceless piece, or the quark energy momentum tensor. Then you want to isolate the matrix elements by fitting the time dependence of the correlation function. So those ratios that I showed you before, they'll get you at these types of matrix elements. Proton, energy momentum tensor proton, but that, remember, gave you this expression here, a linear combination of the generalized form factors. So after computing this for different choices of P, the momentum, S, the spin, different indices, mu and nu, you'll get, in each case, a linear combination here, and so you need to solve a system of equations to isolate the generalized form factors. You get all 3 of them sort of as a set. Okay, so this is the most gory detail slide. It's just showing you what this looks like. So the types of ratio you can take, this is a 3-point correlation function. It's a function of momentum, the sink time, the momentum transfer, and the operator insertion time. This is the 2-point correlation function, just a function of momentum and time, and these are all 2-point correlation functions. These indices here is a spin. This R is indexing the operator insertion choices. So you can't just pick any indices, mu and nu. You've broken the symmetries down to the hypercubic group, from the Lorentz group down to the hypercubic group when you're on a lattice, and that can induce mixing between things that wouldn't mix under a normalization in the continuum. And so you need to be very careful to choose operators that live in irreducible representations of the hypercubic group that do not mix, and particularly do not mix with any other dimensioned operators such that you would get power divergent mixings in the lattice spacing, because that would mean that as you make the lattice spacing small, the contamination gets worse and worse and worse. So you have to be very careful on your choices, but you can choose safe irreducible representations. You put it all together and you get something that, as you make all the times far apart from each other, you isolate the matrix element you're interested in with some kinematic factors. Okay, so you do all of these things. You have ultimately really a monster system of equations to solve once you've done all of the fits. So you have something like 20,000 different ratios for all of these different kinematic choices. You can average them down into groups that have the same linear combination of the generalized form factors. And so these are averaged down ratios. If you sum them over different operator insertion times, you get something that's particularly amenable to doing automated fits on. You get something that is linear in time in the matrix elements you're looking for, plus some constant that you don't care about. So you can, in the end, work your way down to 20,000 linear fits. And of course, then you need to vary fit ranges, do model averaging, what if you include excited states beyond the linear term, and so on. But this is sort of how the statistical goose is cooked as we're getting close to Thanksgiving. Then you solve the system, then you do the non-perturbative normalization, and you can move on. What do these look like? These are just two examples of these 20,000 type fits that you're doing. These are all showing different source sink separation times. You can see as these numbers get larger, the error bars get larger, but you can do multi-state fits to these bumps here. If you do the summation thing, you see that these look very linear. You can do linear fits here. This is the same thing as exponential fits here, linear fits on this side. Okay, so you can extract all of these thousands of numbers, which would be the blue highlighted values, and you can put them together, solve the system of equations after you've put the renormalization in, which I'm really glossing over in the interest of time. And at each value of the momentum transfer, you've solved an overdetermined system to isolate. This is the A and J generalized form factors. D's on the next slide just because it didn't fit. Okay, so doing all of that, you can really decompose, and this is the first such decomposition, these generalized form factors into up quark, down quark, strange quark, gluon pieces. Here's each quark piece individually, up, down, strange, for the A generalized form factor, for the J generalized form factor. Where are the things we can hang on to? If we've done it right, this total here should be 1, because this forward limit value at 0 should be the momentum fraction. So this says the fraction of the momentum carried by the sum of all the quarks is about 0.5, by the gluons is about 0.5, the total is 1, as it should be. So that's a result of the calculation not put into the calculation. That's very reassuring that everything is under control. Similarly, this value here should be 0.5, that should be the total spin. These numbers here should be the fraction of the spin contributed by the quarks and the gluons, or if you like, up quarks, down quarks, and strange quarks, all separately. That's also consistent with 0.5. Excellent news. More interestingly, what about the D term? And so here, for the first time, we're able to see, well, what is this? All of the different quark pieces. The uncertainties are pretty large once you get down to 0 here, but it looks like the sum is, a fairly large -4-ish number. What should it be? Hard to know. For the pion, you can do some sort of chiral effective field theory type predictions. You get a somewhat large negative number. This is all consistent with what you might expect. This is the first time you can get this decomposition. How do we now compare to experiment? How do we put this together to learn something new about the proton structure? So here, now that we've done the lattice calculation, we can go back to that very first experimental measurement. They measured the up plus down quark combination D term. They used it as a proxy for the entire D term, but what they really measured was the up plus down piece. We can create the up plus down piece from the lattice data and compare. So these were the 5 data points from experiment. The gray band here is much wider than the gray data points because there's an overall uncertainty in the normalization of the experiment. So these are showing one uncertainty, the band is showing the overall normalization uncertainty. The red data points are the Lattice QCD results. And you can see, again, in these sort of early days, first constraints, there's again a nice complementarity. The experiments have much more potential to get tight error bars here, and that's what's harder for the Lattice QCD calculation, just because there are fewer combinations. At low momenta, there are fewer combinations that you can write down that give the same total momentum when you have discretized momenta. So there's fewer constraints. We can get tighter constraints out here where the experiment can't get. So again, it's sort of the combination of theory and experiment is what's constraining this total form factor most precisely at the current time. Okay, so that was the quark piece. We can compare theory to experiment. The gluon piece, there have since then been experimental measurements of the gluon piece for the first time also. And so these were 2023. So this is showing the A generalized form factor and the D generalized form factor. And these different colored bands are all different analyses of the same experimental result. So the experimental constraints, they don't actually get at A and D, they get at essentially a combination thereof that can't be fully separated. And so when they did the analysis of the experiment, they used some model input to separate out A and D, and they used several different models to do that. There was what they're calling method 1, method 2, and then a third independent group did another reanalysis, which is essentially a corrected version of the green. Method 2 becomes this purple one. And what you see is the Lattice QCD results in blue agree much better with one version of the analysis of the experimental data than another. And so again, a nice complementarity between theory and experiment. This sort of gives some insight into the type of assumptions that should be made in analyzing the experimental data. Okay, so then you can go and put it all together and answer this question of radii of the proton. And so what I'm showing here is this is the charge radius of the proton that's known very precisely. Here I'm showing quantities known as mass and mechanical radii of the proton. And how they're defined is really, I mean, it's shown here, they're defined from energy and longitudinal force densities. So you start with an energy density and from that define a radius, start with the longitudinal force density, from that define a radius. How do you define an energy density? This really goes back to the matrix element of the energy momentum tensor. That's where you start to get what you would write down as an energy density, but it's essentially this linear combination of the different generalized form factors can be interpreted, or their Fourier transform can be interpreted as an energy density. And so if you define these mass and mechanical radii, what you see is overall the scale is quite comparable to a charge radius. If we really look at these different pieces, so the blue is the lattice calculation of the gluon mass radius. The 3, purple, orange, and green, are from the 3 different experiments here, or the 3 different analyses of the same experiment here, what you get if you look at the mass radii from those. The red is the lattice calculation of the quark mass radius, then similar lattice calculation of the gluon mechanical radius, lattice calculation of the quark mechanical radius. And these all predictions ahead of first experimental results. So these, there have not been experimental determinations of yet. This one, that gray point came out, like I said, within a couple of weeks of our prediction, came the first experimental determination of the quark mechanical radius, which is in very good agreement with the theory result. So this is sort of an exciting development, and we're waiting for first experimental constraints on these ones here. Okay, so I think the qualitative thing to take away from this is defined in this way from energy and longitudinal force densities. It looks like the gluon radius is bigger than the quark radius, which again, it's a definition-dependent question, so I say define in this way. But that's a fairly interesting qualitative statement that we couldn't have made a year ago. Okay, so what about going further from here? This is sort of an interesting side project. Well, what about glue balls? So glue balls are, potentially non-hadronic states, so you have really glue degrees of freedom instead of your mesons with quantum numbers of 2 quarks and baryons with the quantum numbers of 3 quarks. And if you can go and measure things like about the gluon structure of hadrons, maybe you could measure the gluon structure of postulated glue balls and use it as a smoking gun for, well, is it really a glue ball with gluonic degrees of freedom or not? Is it something misidentified? And so we said, well, can we go and calculate aspects of the gluon structure of glue ball states, which you can create in Lattice QCD? And, well, potentially. So this is unpublished, it's on the archive, but in a proceedings, but unpublished, still in progress. These are showing gluon generalized form factors A and D for a variety of hadrons, so delta, nucleon, rho meson, pion, and a glue ball state. And okay, within these uncertainties, it looks fairly similar to the gluon generalized form factors of other hadrons, but this is a direction that we think is quite interesting to go in. Okay, so with the second part of the talk, I want to give another example, which is really living in this part of the structure diagram in the transverse momentum-dependent parton distribution functions. And so when we go from the parton distribution function, so just these number densities with some longitudinal momentum fraction, to the transverse momentum dependent parton distribution functions, where we have also a transverse momentum dependence, as the name suggests, you have more complicated distributions with more free parameters, and as it turns out, more evolution equations. Just to give you a bit more of a sense for where these TMD PDFs come up, well, they will come up in a Drell-Yan scattering process where quarks from two protons here annihilate to give a photon, which then decays into two leptons, or here in a semi-inclusive deep elastic scattering process, here you get 2 copies of the TMD PDFs, here you get just 1, so that's sort of the types of experimental processes they appear in. To be a little bit more precise, let's put all of the different variables in it now. If we look at Drell-Yan, which was this scattering process here, right? 2 protons with 2 different momenta, PA and PB. You can write down that there's a tilde, there's some soft factors and things I'm ignoring here, but you get 2 of these TMD PDFs. This is the longitudinal momentum fraction of the struct parton. This A label is for proton A, this one for proton B. You have these transverse scales BTs, which are the Fourier transforms of the transverse momentum, KT. You have a renormalization scale mu, and there's an additional scale. That additional scale is called the Collins-Soper parameter, and if you like, it's related to the hard scale of the scattering process. So it's defined here. And that additional scale, the evolution in that scale, is non-perturbative, even when everything else in the problem is perturbative. So this is your sort of classic evolution equation that you have also for parton distribution functions. By evolution equation, I mean the dependence on changing that scale, right, is here governed by this quantity. The dependence on changing the second scale that appears only for the transverse momentum dependent PDFs is called the Collins-Soper kernel. It also can be identified as a rapidity anomalous dimension. Okay, so this evolution kernel, it governs the evolution of the TMD PDFs in the second scale. It's actually needed if you want to do lattice QCD calculation of TMD PDFs. It's perturbative at very short distances, but it's non-perturbative at long distances, which really drives asking whether you can do a lattice QCD calculation of this quantity. And okay, why might you care? So there's now sub% precision in Drell-Yan at the LHC. The lack of knowledge of this thing really limits theory predictions to much lower precision. This is important there. Another, and really that lack of knowledge is what I'm isolating on this slide here. So this is really showing estimates of size of the non-perturbative contributions to the kernel. So this is that scale BT, or 1 over the scale BT. That's your impact parameter, if you like. And these are estimates of the uncertainty on this Collins-Soper kernel. You can see as you come to the left, it's really not well known at all. What that means is if you look at phenomenological constraints of the kernel, as soon as you go to BT being large, this is 1 over BT, this is BT. That's why it gets unknown to the left here and to the right here. There are significant discrepancies between phenomenological constraints on this quantity. Okay, if you don't care about Drell-Yan at the LHC, maybe you care about things like W mass measurements. So this is maybe less exciting since the very recent CMS result, but this Collins-Soper kernel is also input into things like measurements of the W mass at the Large Hadron Collider. So this uncertainty band here on the Collins-Soper kernel, this is again an estimate of uncertainties in the non-perturbative region, feeds back into this sort of a profile of percent to 10% level uncertainties in the relevant distributions for this scattering process, which is how the W mass was measured. And so that then feeds into the analysis of experimental data. And so particularly when you have tensions like this LHCb measurement over the last couple of years with the previously accepted standard model values, you start to look into all of the details, which includes the uncertainty on this particular quantity, right? So this is one of the things that motivated saying, can we go and measure this thing for the first time? Okay, so this is again an area where there's been very rapid progress. This is the status from early 2023, so just a year and a little bit ago. And we did very, very first calculations of the Collins-Soper kernel, which were rapidly followed by other groups. This is this BT parameter, this is the Collins-Soper kernel. You see small error bars and things disagreeing. right? And that is because these were first calculations that did not have all of the systematics under control. They were on a single ensemble. They were, one lattice spacing, one volume, one set of quark masses that are not necessarily the physical quark masses. So if you saw this plot uninformed, you would think Lattice QCD has no way of constraining this. This is all inconsistent. But that's because all these error bars mean something different. A few years later, the evolution was you see much bigger error bars. That's because now other uncertainties are being accounted for, and some steps towards consistency here. But the evolution from this to this year has really been that we've been able to do the first actually rigorously systematically controlled calculation of this Collins-Soper kernel from first principles for the first time, with a precision that's beginning to be able to differentiate between different phenomenological models in the relevant regime. Okay, so some hints on how you might do this. I don't want to go into sort of too much gory detail, but I'll show you a little bit to appreciate what's happening here. Is these TMD PDFs are defined by light cone separated operators, and we're living in a Euclidean spacetime, so you can't write down anything that has a light cone separation. So you have to get a little bit more creative. So what you can actually show is that if you want to take a matrix element of a staple-shaped Wilson line operator along a light cone, you can't do that. What you can do is take a matrix element of a staple-shaped Wilson line operator not on a light cone, and at large boost, or with a perturbative matching, you can relate the matrix element of this, which you can calculate, to the matrix element of this, which is what you really want. And so what you end up being able to write down is quasi-TMDs, which are not TMDs, but they're quantities that you can access in Lattice QCD and Euclidean spacetime, a perturbative matching coefficient, a non-perturbative soft factor, the evolution kernel comes up in here, and the PDFs that you're actually trying to constrain, right? So it's sort of a multi-step matching process. This perturbative matching will only be good in a limit where you have very large momenta. Okay, so then in the end, you can get at this Collins-Soper kernel from, again, you can take ratios of things that in certain limits give you the matrix elements you're interested in. These are quasi-TMD PDFs. These are renormalization factors, taking you from a lattice scheme to an MS bar scheme. Calculating these involves both a non-perturbative calculation and a perturbative piece. You then want to take Fourier transforms, take a ratio, take a log. This is a ratio of pieces at different momentum, P1 and P2. That's different, very large boosts. They need to both be large, but both sufficiently different. Then there's a perturbative matching piece and power corrections. Okay, so clearly lots of moving pieces in a calculation like this, but the principle, the underlying principle is sort of the same. You need to find some way of being able to write down a matrix element of something that you can compute that can be related to the physical quantity you want to constrain. It doesn't have to be the same thing, right? But it needs to be something that you can connect. And so that's where some of the creativity comes in, really, is how do you get at the physics you want? And it's not necessarily directly, right? But that doesn't matter, because what you're really studying is a quantum field theory, just doing field theory calculations numerically, and the question is what matrix element quantities will constrain the target physics. Okay, so there's a number of steps. This is really PhD work of my excellent student Arthur, who's on the job market this year, and some former MIT postdocs who now have independent faculty positions. You calculate the bare quasi-wave functions, you do renormalization and matching, a Fourier transform to momentum space, you take the ratio, you need to worry about the perturbative matching, the power corrections, then you want to extrapolate, the lattice spacing goes away, so the continuum extrapolation, the infinite volume extrapolation, and so on. So we've done this just this year, able to do all of these steps, including the continuum extrapolation to get a first controlled calculation. Okay, so what does that really look like? So the types of operators that you're computing is you can take a hadron state, say a pion. Since this thing's state independent, you can take the easiest state. You can take a pion state at some large momentum p. You put in an operator, which is a Wilson line, a staple-shaped Wilson line with a Euclidean space separation, and you can put the vacuum here. So you really try to get the most precise possible matrix element you can. You can compute two-point correlation functions also. So you create your state, you annihilate it in this staple, and then you can form ratios. Again, This ratio looks a little different from some of the other ratios I showed, but it's the same sort of idea. You form a ratio that isolates in the large time limit the particular matrix element that you care about. Okay, so clearly there's a lot of different parameters here. There's how long do you make the staple, how asymmetric do you make the staple, and all of these things you have to either extrapolate away or treat systematically. Okay, so you calculate these bare quasi-beam functions, and this is what they look like. There's something like 600,000 individual fits that go into making plots like this. This is showing a few hundred of them. Each of these points comes from fitting a very large amount of data. So the fact that these seem to lie on smooth curves is already a very good sign for your analysis. When you unblind and you see that they all line up, that's a very good thing. So this is at some particular transverse separation BT, at some particular value of the momentum transfer. That's what this NZ is. Okay, we then want to do renormalization and matching that I'm not going to go into too much detail about, other than to say you can do the renormalization non-perturbatively, which is pretty nice actually. You can say, okay, I'm going to do what I would do if I was doing a renormalization by hand. I'm going to say, calculate the matrix element of this in a quark state, and say that should be equal to its tree level value. Right? That's what you usually do. You can do that non-perturbatively also. It's in a particular scheme that you then have to perturbatively match to something like MS bar. You want to calculate, that's this non-perturbative renormalization, a perturbative matching part. Renormalization, as it should, doesn't really change things by more than about 10%. That's again very reassuring. It's really the mixing that's changing things here by about 10% mixing between different Dirac structures. You take a Fourier transform to momentum space. As you could see, these have been consistent with 0 in the tails, so you can do things like discrete Fourier transforms with good systematic control. These should converge to 0 outside the range of 0 to 1, and as you can see, as you make the momentum scale larger, going from purple to yellow, they get closer to 0 in these tail regions where they should eventually vanish. Again, sanity checks on the data check out. Then you take ratios of these pieces, perturbative matching piece. I'm not going to go through these details here given the time. And you get things that look something like this. So this, at first, might not look like something that you can extract a Collins-Soper kernel from, but in fact, these are different ratios of different momenta, and you can fit, and within this region here, they should be fairly flat, which they are. You can fit the remaining differences between these momentum ratios by fitting to power corrections and discretization artifacts, by doing the same calculation on lots of different lattice ensembles with different lattice spacings and volumes, and knowing the power series that the corrections should have. So here is just looking at the different momentum combinations as a function of BT more clearly. These differences here are then what you're going to try to fit by fitting power corrections and discretization artifacts. If you do that, if you take different orders of perturbative matching, you get these different results for the Collins-Soper kernel. This is leading order, next to leading order, unexpanded next to leading order, next to leading log, next to leading order, next to leading log, and so on. You can see differences here below at short BT scales. You see differences at different orders, and those are related to the different treatments of power corrections in these different schemes. There's consistency above, except for the leading order, which is again reassuring that all of these different orders are working as they should. Then you can disentangle and fit the power corrections and go from raw data to artifact subtracted data. And that's what it looks like when all is said and done. So this is showing this BT scale. This is the Collins-Soper kernel. The different colors are different phenomenological constraints on the Collins-Soper kernel. As you can see, in this region out here, they start to be really quite different. The red band here is something that we're pretty excited about that we're able to do for the first time, is fit a phenomenological parameterization to pure theory data to have a pure theory determination of the Collins-Soper kernel to compare to the phenomenological ones. So this is really a first controlled calculation. Others will improve the statistical precision over the coming years, but it's again, a demonstration of the synergy between theory and experiment here now that we're in really a precision era. Okay, so, well, what next? My group's not going to push the precision on that. Now we've figured out how to do it, we're going to figure out how to do something else interesting, which is the gluon Collins-Soper kernel, which, well, from one-loop perturbation theory, in the perturbative region, we know how that compares to the quark Collins-Soper kernel. It should have the same shape, it's just different by a color factor, by a Casimir. But what about in the non-perturbative region? No one knows. It's never been constrained experimentally, but it will be through experiments over the next decade or so. And so we're working on calculating it for the first time. This is with an excellent local postdoc, Yang Fu again, my graduating student Arthur, and some former MIT postdocs who are now leading their own groups. And you can do the same sort of calculation. It's really, really difficult. It's statistically. So these two plots show these quasi-beam functions at the same statistics. This is the quark one that we got those results from. This is the gluon one at the same statistics. So clearly, in order to constrain this properly, some new tricks are needed, not just hammering the computer longer, but we need to come up with some new tricks to do this analysis effectively. But on the time scale of the experiment, we'll have a prediction before they're able to constrain this. Okay, so just to sort of summarize the story, we got into the weeds a little bit, but I hope you have a bit of an understanding of where the various uncertainties come from, how to interpret these types of lattice QCD calculations. And the two results that I really talked about were new, and they're really first lattice QCD calculations of this Collins-Soper kernel that's driving the rapidity evolution of TMD PDFs, and is sort of a hidden input into lots of analyses of interesting processes at the Large Hadron Collider. And we've been able to do a flavor decomposition of these generalized form factors, especially this D term, this sort of previously unknown, some have called it the last global unknown of the proton, for the first time. And so get first constraints on the complete decomposition of the proton's pressure and shear distributions. So we're at this exciting juncture where we're going from, 10 years ago, first precision lattice QCD calculations of the most basic of proton properties, things like its momentum, to really being able to say, on the same timeline as first experiments, more about the internal structure of proton, neutron, and even nuclei that I don't have time to talk about today. Thanks.
You've mentioned that you'll need to take some form of large rapidity limit in computing Collins-Soper kernel.
Large momentum limit.
Large momentum limit.
Large boost of the states that you're studying. Yeah.
Well, is it in the Lorentzian space?
No, so this is when I was talking about you create a state and you insert an operator and you annihilate the state. It's the boost of that state in our Euclidean lattice calculations. It has to be large.
Okay. Thank you.
I have two questions. The first one is that when you're talking about D term, I noticed that there's a mu index, so it means that there's 16 term there. And I wonder that is there any sum rule that we can guarantee that the D will satisfy?
Yeah, so we don't know any sum rules for the forward limit of D. So the this mu nu here is really pulling out, if you make some choice, pulling out a different linear combination of these three. So the D doesn't have a mu nu on it.
But for different mu nu, the D will be the same, or?
Yes. For different mu nu, you just pull out different gammas and different components of the momentum here. But these three coefficients are the same in all cases. The index on the D is just the quark and gluon pieces. So that's where you might hope for a sum rule. For the others, you have a momentum sum rule that the quark and gluon momenta have to add up to 100% of the proton's momentum. For D, there is no known sum rule.
I see. Okay. The second question is about the CS kernel that you mentioned that there's no information about the non-perturbative region. Is that possible to constrain? Because you compute the perturbative region, is that possible to constrain the non-perturbative region from some lattice, from some Collider experiments?
Yeah. So that was. So these are phenomenological constraints of the Collins-Soper kernel. So they model it, have some parameterization that's then fit to various experimental data at different scales to try to constrain this scale evolution. But as you can see, once you get to the non-perturbative region, there's inconsistencies because there's not really good data to constrain it in this non-perturbative region. Right, so that's why theory calculations that can get at this region are particularly interesting because it's difficult experimentally. And also, if you didn't have to constrain constrain the evolution from the experiments, you could use the theory evolution to compare the experiments and use it as input, go the other way around, right?
I see. Okay, thank you.
Thank you for the great talk. I guess you mentioned, you emphasized that you're doing the lattice QCD computation on Euclidean lattice. And I wonder, like, is there a reason for it? And how do you relate that to actual experimental data?
Yeah, so you have to go to the Euclidean lattice because essentially a sign problem, right? If you have the I in the exponential, it becomes something very difficult to do numerically. So there are the efforts to try to do, to do that mostly using quantum devices, but using sort of the classical sampling algorithms, you have to go to Euclidean space. How you compare to what you measure experimentally? Well, it all goes back to just thinking about it from the field theory perspective. All you're doing is a Wick rotation, right? And you know how things relate under Wick rotation. You know you have to be careful when you're matching to put I's in all of the right places. If you have to transform your momenta appropriately, right? So in this equation that I just had up on the board, when you're writing down the Euclidean energy momentum tensor versus the Minkowski energy momentum tensor, you have to be careful how all of these pieces work out, that you get the right signs, the right I's, but that's all just mechanical matching. If you know what you're studying in the Euclidean field theory, you can convert to what you've computed. That doesn't mean that everything you might want to compute in Minkowski space is accessible on the Euclidean spacetime, right? So things like the Collins-Soper kernel, we had to go through a big rigmarole there of, go off the light cone, boost to the light cone, do perturbative matching to try to get back to something that's very easy to define in Minkowski space. Similarly, things like real-time dynamics, it's really hard how you get that from a Euclidean space matrix element. But the things you get in Euclidean space are well-defined, and you can match them to something. Whether that something is what you actually want is the big question.
Yeah, thanks for the great talk. Maybe I have a little broad questions. You mentioned that usually in Lattice QCD, we will simulate in a large quark mass because that's more convergent and we extrapolate the result to the lighter mass case. I was wondering if there's possible way, why we cannot do the massless simulation, or is there a possible way to do the massless Lattice QCDs? Thanks.
Yeah, so these days, calculation of things like proton structure are using quark masses corresponding to a physical pion mass. So hopefully interpolation rather than extrapolation needed, unless you're doing things like nuclear physics where you're really pushing the boundaries computationally. It's very, very hard to do that. So these were with physical quark masses, all of these calculations. Going massless, I mean, the lighter the mass gets, the more and more singular all the matrices you need to invert get. So getting lighter and lighter, your computational cost explodes doing it via an approach like this. So, getting to physical masses has been a great achievement over the last decade or so. It's still not there for absolutely every calculation. You need to do something qualitatively different if you want to study a massless case.
Yeah, I was curious about the physical pion mass business. Has this given any insight into chiral perturbation theory and how they all go together?
Yeah, I mean, not sure insight in so much as, so when I was a graduate student, matching lattice QCD results to chiral perturbation theory was hard. You had to do sort of devastating things like finite range regularization or something because the masses rule at a scale that's not really, not really in the regime of validity. Now, however, we use chiral perturbation theory all the time to, interpolate to the physical mass, to extrapolate a last little bit. So I don't know, deep insights?
Yeah, the question was really whether you're at the stage where the analysis, where the insights go the other way and telling you more about convergence of chiral perturbation theory calculations and things like that.
Barely. Barely. I'd say in some cases, yes. So some of the calculations of like I didn't show them, but so the pion gravitational form factors have been pretty interesting from that perspective because there were chiral perturbation theory predictions that you can then go back and the precision's starting to get to the point where you can answer those sort of questions, but it's sort of on the edge.
So you mentioned matching with the perturbation theory. I was wondering whether for these form factors, whether the non-perturbative dispersion relations have also been used in this context to help, like, and continue or things like that.
I don't think so. Not that I know of for these particular form factors.
Thank you.
Well, let's thank Fiona again and see her on Thursday.
Thank you.